Let's take a shot at equilibrium. Equilibrium is one of those terms you'll see in many different subject areas. You can see it in environmental equilibrium, um, biological equilibrium, and in this case we're going to talk about chemical equilibrium. Now, equilibrium just itself means a balance in your system, a balance between components. And in the case of chemical equilibrium, it means our reaction has reached a balance. So what that means is when you're having a reaction take place, normally reactants turn into products. But some reactions are reversible. As your products are produced, it also simultaneously falls back into the reactants that created it. So let's say if I have reactants A plus B and I mix those together, I create product C. So A and B synthesize product C. But at the same time, simultaneously, that C product is also decomposing back into A and B. So this reaction is reversible. It's two ways. You have a reaction going forward and you have a reaction going backwards. So we could say chemical equilibrium is when the forward rate of reaction is equal to the reverse rate of reaction. So the forward rate of reaction is equal to the reverse rate of reaction. That means you will not see any observable change in your concentrations. No observable change in concentrations of chemical species. The species being, in this case, A, B, and C. So if A were 3 molar, B were 2 molar, and C were also 3 molar, that's what those concentrations are going to stay at once this reaction reaches equilibrium, even though the reaction is still taking place. So A and B are producing C, and C is producing A and B, but since the concentrations of those species aren't changing, you can't actually see any reaction taking place, even though it is actually happening. Let's think about this in the terms of a graph. Graphs make things easy to visualize, so let's try to make this an easy visualization. We'll say the green line is my reactants, the blue line is my products. Our y-axis will make percent concentration, measured in moles per liter. So at the bottom we have 0%, at the top we have 100%, and we also got 75% and 25%, and of course 50% in the middle. Our x-axis, we'll just call it time. It can be seconds, it can be minutes. It's kind of irrelevant for us right now, but x-axis will be time. So at the start of a reaction, before you mix all your reactants together, what would you think the percent concentration of your reactants would be? Well, that would be 100. You haven't consumed any reactants, so at the start of your reaction, your reactant concentration is 100%. Since we haven't created anything, that means your product concentration is 0%. Now, Once you take the reactants and you mix them together and actually cause a reaction to take place, what happens to the concentration of reactants? Well, as reactants are consumed for your reaction, it goes down. The concentration of those reactants go down over time. Opposite to that idea, the amount of product, the concentration of our product, since we're actually producing products now, that percent concentration, it starts to go up. So reactants are making products, and the concentration of products is going up, concentration of reactants is going down. But this particular reaction, it goes both ways. Reactants produce products, but at the same time, products are also producing reactants. So eventually you get to a point where these reactant concentrations, it levels out and goes flat. You're not seeing any observable change in the amount of reactants being produced. Same goes for the products. Eventually this product concentration also levels out. And now that concentration is no longer changing either. So the concentrations aren't changing, so it may appear that the reaction isn't proceeding forward, but in fact it is. It's just the forward rate of the reaction is now equal to the reverse rate of the reaction, and then there's no longer any changes to the concentrations of either the reactants or the products. So this graph will tend to go flat. And that is when equilibrium occurs. So at this flat portion, we have chemical equilibrium. Now some people ask in the graph, what about this intersection where the lines cross? If these lines happen to cross, and sometimes they do, sometimes they don't, it means nothing. This particular intersection on your graph is irrelevant. It's nothing. It's just coincidental. It has nothing to do with anything. Once equilibrium is reached and you have a set concentration between your reactants and your products, there is a relationship between that amount. And that relationship is called the K constant. The K constant. You may see it abbreviated as KEQ for the equilibrium constant. You may see it as KC for concentration equilibrium. You may see it as KP for pressure equilibrium, Ka for acids, Kb for bases, so on, etc. But the main idea, though, is this K constant. The K constant is the relationship between the products and reactants at equilibrium. So the relationship between products and reactants. And since it's a relationship, that means there's a formula. Now this formula is a formula to figure out a formula, so consider it a shell formula, and it'll make sense in a little bit. But your K formula is K equals the concentration of products over the concentration of reactants. And do notice I put these in brackets. Brackets means concentration. If you put parentheses, that means pressure. It does make a difference later on. Now what that K means, it tells you whether or not your reaction is going to favor products or if it's going to favor reactants. So if K is greater than 1, your reaction will favor products. So your reaction is going to be more inclined to produce a lot of product, and you're going to have a greater loss of reactants in their concentrations. If your K value is less than 1, it's going to favor reactants. That means when you're doing your reaction, at the start of it, you're not going to lose as much concentration of your reactants. and you're not going to produce as much concentration of products. And if K equals 1, well, that's just equilibrium. There's a balance between the two. All right, and just a little bit more to note. Equilibrium is affected by different conditions. So equilibrium can be shifted, that K constant value can be shifted, or your equilibrium can be shifted by pressure, temperature, and concentration changes. So equilibrium is affected by concentration, pressure, and temperature changes. And that's going to be called Le Chatelier's principle. We'll get into that more in detail later on. But if you change one of these conditions, it changes your equilibrium point for a reaction. Also worth noting, equilibrium is not affected by liquids and solids. So if your species, your chemical species, are in a liquid or solid form, it's going to be left out completely. So liquids and solids do not affect equilibrium. So if you see a liquid or a solid in your reaction, ignore it completely, take it out. It is not a part of the problem. Before we move on to actually solving equilibrium problems, we need to go a little bit more in detail about this formula. Because like I said, this formula right here is a formula for a formula. Let's say I had an arbitrary reaction. An arbitrary, just made up reaction. So we got A plus B yields C plus D. Let me just throw in some balanced equation. These are just random numbers I'm just popping in off the top of my head. So let's say we had this reaction in an equilibrium problem. First thing we need to do is we need to write the formula for this reaction. And we know the formula is K equals the products over reactants. All right, so I use this idea to create a formula. So that's going to be K equals products. So what are my products? My products are C and D. I know they're products because they're on the right side of the arrows. So the products is C and D. So my products are going to be C and D. So it's going to be the concentration of C raised to a power, for now I'll just call it C, times the concentration of D, also raised to its own power, so I'll call it D. And I'm using lower cases for my powers, upper cases for my species, over the reactants. So my reactants are going to be A and B, so the concentration of A raised to A times the concentration of B, and it's raised to its own power, so that's going to be little b. So this formula is the formula you should keep in your notes, because this is going to be your actual formula. This formula is more of the formula we use to derive this central formula. So you can keep up with this one if you want to, but the real formula you want is this concentration of C and D over the concentration of A and B, and then you can manipulate it in your work as you go from there. Alright, so let's carry on. So now that I got my actual formula, I need to create a specific formula to my reaction. So what this first formula really was a formula to get a formula to get a formula. So now we can actually write the real formula for this reaction. Alright, let's see if we can't write this specific formula. So I know it's K equals products over reactants. Well, my products are C and D. In this specific reaction, it is literally C and D. It won't always be like that, but for now it is. So the concentration of C, so that'll be my first product. In this case, it is C. And it's raised to a power. That power is its balanced equation. So that's 3. It's going to be cubed. Times the concentration of D, in this case the second product, and in this specific case it is actually literally D raised to its power. Well, that's just a 1. Over the reactants. Well, reactants are A and B. Your two reactants. In this case they literally are A and B. So A raised to its power, which is 2, so it's going to be squared, times B, the concentration of B raised to its power. That's going to be a 1. So this formula here is your actual specific formula you will use for that particular reaction. So this formula came from this base formula, which came from a shell formula. Hopefully all that wasn't too confusing. But if it was, and the main thing you want to take from it is this formula right here is your actual formula you want to keep in your notes. C and D are the products, A and B are the reactants, and the lowercase letters are the balanced equation coefficients in front of those corresponding letters. Alright, let's practice writing the formula a few times because you gotta have that down before you can proceed on any past this point. If you can't write the formula, you're just going to be dead in the water. So we're going to write the equilibrium formula for each reaction. Alright, so our base formula is K equals concentration of products, which we know to be concentration of C to its power times the concentration of D to its power over the reactants, which is going to be concentration of A to its power times the concentration of B to its power. Now all 4 of these cells will not necessarily be filled in. Not all 4 of those cells will necessarily be present. Like for instance, this first reaction only has 3 species. My formula has 4 cells. I'm not going to use one of them, and that's fine. Alright, so let's do this thing. Let's write this formula. So K equals, got 2SO2, O2, 2SO3. First thing you always want to do is check your state of matter. Gases and aqueous solutions are the only thing that matter. All these are gases. All of them will be included in my formula. Next, make sure your equation is actually balanced, because if it's not balanced, then you're not going to have your powers. And we are balanced. So let's continue. So products over reactants. Let's do products first. Only got one product. So that's going to be the concentration of SO3. So what I did there is I filled in for C. And now I need a power. It has a 2 in front of it, so it's going to be raised to the second power. There is not a second product, so I'm not going to have D. Move on to reactants. So my first reactant is SO2. So the concentration of SO2, and it's going to be raised to a power, and it has a 2 in front of it, so it's going to be squared. Next reactant, times O2. It does not have a number in front of it, so it's going to be considered 1. I'm just going to leave it as is. So there's our formula. Let's do another one. Got H2 plus I2 yields 2HI. All of them are gases. Our equation is balanced. K equals products over reactants. My first product is HI, so the concentration of HI, it is raised to a power, so I need a number, and that number is 2, over reactants. My first reactant is H2. It has a 1 in front of it, so no need for a number, no need for a power, times the concentration of the next reactant, which is I2. I need a power. It's a 1 here, so it's understood to be 1. And there is our formula. Hopefully this is starting to click for you if it wasn't. So it's always products over reactants. The balance equation is the superscript or the power to which you raise it. All right, next one. We got 4 species. Balanced equation. I notice one of them is a solid. Solids do not affect equilibrium. I'm completely going to ignore PCl5. So K equals products over reactants. 2 products. First product is HCl. Concentration of HCl raised to the power of 2 because of its coefficient times the concentration of POCl3 raised to its power. Well, that's just a 1, so it's understood. Over reactants. Only got one reactant because we're ignoring PCl5 because it's a solid. So the concentration of H2O raised to its power, and there's a 1 here, so it's understood. So that is writing the formula for equilibrium. Let's look at it one last time. K is products over reactants. The products are the individual species raised to their balance equation coefficient. So K equals products over reactants. The balance equation coefficient is the power they're raised to. All right, let's continue on. So now that we know our formula, we can start solving for unknown information. So this first problem wants us to solve for the equilibrium constant, or the KEQ, or just K, of the following reaction. If we got 4 moles of SO2, 5 moles of O2, and 4.5 moles of SO3, and they're in a 2-liter container at equilibrium. So we're looking for the equilibrium constant, and we have equilibrium concentrations. Now, equilibrium has to be in molarity or it has to be in pressure. So the first thing I got to do is convert these moles to molarity. Well, molarity, if you remember, is moles divided by volume. So I got 4 divided by 2. That's going to be 2 molar for this first species. 5 divided by 2, that's going to be 2.5 for oxygen. And 4.5 divided by 2 is going to be 2.25 molar for SO3. So there are our concentrations. So now we need to figure out what's the K constant of these concentrations. What's the equilibrium constant? So our formula is K equals concentration of products over reactants. Concentration of products over the concentration of reactants. Alright, so let's see if we can figure this out. Start with your products. Concentration of your products. That's going to be the concentration of SO3 is raised to the second over the reactants. There's only one product, so we move on to reactants. First reactant is SO2. It's raised to the second times the concentration of O2. It's to the first. Alright, there's our specific formula for this reaction. Now, all we got to do is take our concentrations and plug into that. So the concentration of SO3 is 2.25. And it's going to be raised to the second over concentration of your reactants. SO2 is 2 molar, and that is raised to the second times the concentration of O2. O2 is 2.5, and it's to the first. Now we just got some basic math. So 2.25 squared is 5.06. 2 squared is 4, and then times 2.5. So simplify that down a little bit more. 5.06 over 4 times 2.5 gives me 10. 5.06 divided by 10 gives me 0.506. There is our answer. K does not have units, so it's just a value. And since K is less than 1, that means this reaction is going to favor reactants, which that'll come into play later on. All right, let's look at a real problem. Now we can write our formula. Now we kind of understand what K means. We can do a real problem. So solve for the equilibrium concentrations. If the initial concentrations are hydrogen is 1 molar, fluorine is 2 molar, and hydrogen fluoride is 0 molar. We have a K constant of 110. Since it's 110, that means we're going to favor products. All right, key words here. Initial concentrations. When you see initial concentrations and you have some values for that, that means you're going to do what's called an ICE table. Some people also refer it to a RICE table. So I'm going to set up an ICE table. And like I said, some people refer it to a RICE table. R would stand for the reaction. I stands for the initial concentrations. So what are the initial concentrations? H2 is 1.0. F2 is 2.0. HF is 0. All right, make sure, check your states of matter. Everything is a gas. Everything will be used. Make sure your equation is balanced or balanced. Next step, C stands for change at equilibrium. So at change at equilibrium, you're going to say how much these concentrations are going to change by. So reactants will always be lost, so it's going to be a minus. Your coefficient tells you how much. There's a 1 here, so there's a 1. And X is by the unknown value that's going to change by. So let's look at that one more time. So the change at equilibrium, how much this concentration is going to change by, since it's a reactant, it's always going to be lost. It's going to be lost by 1 times the amount, and that amount we don't know yet. We got to solve for it, so that's going to be X. So let's do F2's. It's a reactant, so it's lost. It has a 1 in front of it, 1 coefficient, so it's going to be lost by 1 times the amount, and that amount, I don't know, so it's going to be X. So the change of equilibrium, the change at equilibrium will always have a sign, a number, and an X. So let's do the product now. You're always going to gain product from your initial concentration, so your product will be plus. It's going to be changed by its coefficient, which is a 2, so it's going to be changed by 2 times the amount. But what's the amount? We don't know. That's X. So reactants, again, are minus 1X because it's a reactant, it's minus. There's a 1 coefficient, X is always there. Fluorine's a reactant, it's minus. Coefficient's 1, X is always there. HF is a product, so it's plus. It has a 2, so there's a 2, X is always there. E stands for the equation at equilibrium. So this is what you're actually going to plug into your formula in a second. To find the equation at equilibrium, you take I and combine it with C. So 1.0 minus 1x. So that means fluorine is 2.0 minus 1x. And that means HF is 0 plus 2x, or just 2x. Alright. Hopefully that ice table didn't mess you up too bad, but if it did, make sure you watch the practice problems video where we practice out a couple of these ice tables. Alright, now that we got the equations at equilibrium, we can set up our formula for this specific reaction. So K equals products over reactants. Concentration of products over the concentration of reactants. So K equals, well, what's my product? My product is HF. So concentration of HF, and it's raised to the second, over the concentration of H2 is to the first, times the concentration of F2 is to the first. So there's our formula. Now all we got to do is take the equations at equilibrium and plug them into our formula. So let me scroll down a little bit so I got room to work. So K equals, now K, we have a value for it. The problem said KEQ is 110. So our K is 110. So we're going to plug 110 in for K. So K is 110 equals the concentration of HF. HF is 2x, and it is to the second, or squared. So H2 is 1.0 minus 1x. So 1 minus 1x. Concentration of F2. F2 is 2.0 minus 1x. So 2 minus 1x. Alright. Now we got some algebra. And we need to solve for x. So to do that, I'm going to put 110 over 1. Now I'm going to simplify this down as much as I can. So 110 over 1 equals 2x squared. Well, 2x squared becomes 4x squared because 2 squared is 4, x squared is x squared. 2x squared gives us 4x squared. Over 1 minus 1x times 2 minus 1x. Well, looks like we're going to have to full that one. So let's see here. 1 minus 1x times 2 minus 1x. 1 times 2 is 2. 1 times minus 1x is minus 1x. Minus 1x times 2 is minus 2x. Minus 1x times minus 1x is positive x squared. Combine like terms, 2 stays the same. Minus 1x minus 2x becomes minus 3x. X squared stays the same. So this equation needs to be put under 4x squared. So x squared minus 3x plus 2. Alright, now we're getting somewhere. Now we can start solving for x still. So let's cross multiply. So 1 times 4x gives me 4x squared. 110 times x squared is 110 x squared. 110 times 3x minus 3x is minus 330x. 110 times 2 is 220. Now we need to add like terms. Minus 4x squared, so that cancels, leaves me with 0. Minus 4x squared is 106x squared minus 330x plus 220. So now we got to solve for x still. That looks like some quadratic equation. I like to label mine so it makes it a little bit easier. So I got A, B, and C. Now, quadratic equation, if you don't remember, is negative b plus or minus the square root of b squared minus 4ac over 2a. So now we need to take these values and plug it into our quadratic equation to solve for x. Okay, so I need to take these values. And plug into the quadratic equation. So x equals negative b. B is negative 330. So negative 330 plus or minus the square root of b squared. So negative 330 squared minus 4 times a, which is 106, times c, which is 220, over 2a, so 2 times 106. Now let's simplify this thing down. So negative times a negative makes positive, so that's going to be positive 330 plus or minus square root. Negative 330 squared is going to become positive. So 330 squared is 108,900 minus 4 times 106 times 220, 93,280 over 2 times 106, so that's 212. Let's simplify this thing down even further. So I got 330 plus or minus the square root. Simplify that part down. So 108,900 minus 93,280 gives me 15,620 over 212. Let's simplify that down. So 330 plus or minus the square root of 15,620 is 124.98. And I am rounding that up a little bit. So 124.98 over 212. All right, to find x, we got to do 2 steps. So 330 plus 124.98 over 212 gave me 2.15. So x equals 330 minus 124.98 over 212. Let's do that version, see what we get. So 330 minus 124.98 divided by 212 gives me 0.97. 0.97. So we have 2 values for x. Only one of them can work. So how do we figure out which one works? Well, we got to go back to the start. Back to our equation at equilibrium. We have to plug these x's in. One of them is too big, and when you plug it in, it will create a negative number. We can't have a negative molarity. So generally, the one where you plus, the value where you plus is going to be too big. So the equation where we added is 2.15. If I go back and do 1.0 minus 1 times 215, I'm going to get a negative number. It's not going to work. So generally the version where you plus is going to be too big. So the value where you subtract is pretty much going to be your value. So 0.97 is our value. So we go back to the beginning. So our first equilibrium concentration for H2. So I got H2 equals 1.0 minus 1x. So 1.0 minus 1 times 0.97 equals 1.0 minus 0.97, because 1 times 0.97 is 0.97. So the concentration of H2 is 0.03 molar. So this concentration is 0.03 molar. Now let's solve for the F2 concentration. Do the same thing. So F2 equals 2.0 minus 1 times x. X is 0.97. So 2.0 minus 0.97. So F2 equals 1.03 molar. So this is 1.03 molar for F2. And then we can do the last concentration. So the concentration of HF is 2 times x. So that's going to be 2 times 0.97. So HF is 1.93 molar. It's 1.93 molar. And there is our answers. Those are the equilibrium concentrations. So once this reaction reaches a point where there's no observable change, the concentrations will be 0.03, 1.03, and 1.93 for each respective species. Now I know what you're thinking, that is a lot, and it is a lot. It takes a lot of practice to get equilibrium down. So I highly recommend you practice a lot of these problems. But on the bright side, it does get a little bit easier when your K value is small. This value is pretty large. It's going to favor product, so there's going to be a lot of product made and a lot of reactant lost. If your K value favors reactants, there's not going to be a lot of change in the concentrations of reactants. There's going to be a very small change in the concentrations of products. So one thing to add to your notes. If your K constant is less than 1, but generally really small, if it's something like 1.0 times 10 to the negative fifth or smaller, you can ignore the X on reactants. Ignore the X on the reactants. What does that mean, you may ask? So if I go back to this problem we just took 1,000 years to do, if I were to ignore the X on reactants, that means the sign, the number, and the X, I'm going to ignore it on the reactants. The sign, the number, and the X, I'm going to ignore it. Now just stop and look at this math for a second. If that sign, number, and X isn't there, then we would have never had to fold this. So what's going to happen is it's just going to be 1 times 2. And this is going to be 2. That math is going to be a whole lot simpler. It's going to be 4x squared equals 220. We'll divide by 4, that cancels. You're going to have x squared equals whatever 220 divided by 4 is, which is 55. Take the square root, x equals whatever you get, go back, plug it in. That took me less than a minute in comparison to what we just went through. So if your K value is 1.0 times 10 to the negative fifth or smaller, you can ignore the X on the reactants, and it's going to make your world of equilibrium so much easier. Now with that said, let's actually do one like that. See how much easier it is to do. So we're going to do pretty much the same setup. We got some equilibrium concentrations we're trying to find. We're given initial concentrations and a K constant of a reaction that is essentially the same. 2 reactants making 1 product. We got a 1 to 1 to 2 ratio in your balanced equation. Alright, first thing we need to do is do our ICE table. I stands for the initial concentrations. Our initial concentrations are 2 molar A, so 2 molar, and 3 molar B. It doesn't say anything about C, so that's going to be 0. Your initial concentration of product is typically going to be 0. C is your change at equilibrium. So reactants are always minused by their coefficient and X. Next to B. It's a reactant, so it's minused. By its coefficient, it's 1. X is always there. So let's just run through that one more time. To find the change at equilibrium, reactants are always minused. So A is a reactant, it's minused. Coefficient of 1 tells me by how much it's minused, so 1. And X is by the amount. We don't know it, so it's always X. B is a reactant, so it's minus by an amount. The amount I don't know, so it's X. It has a coefficient of 1, so I put a 1. C is a product. Products are plus. It's plus by amount. This amount is 2 because there's a coefficient of 2. It's plus by 2 times the amount, and that amount I don't know, so it's X. E is the equation at equilibrium. To get E, I put I and C together. So 2 minus 1x, 3 minus 1x, 0 plus 2x is 2x. Alright, there's our ICE table. Our ICE table gives us the equations to plug into our formula. So let's write our formula. K is products over reactants. Concentration of products over reactants. So K is 1.0 times 10 to the negative fifth. Our product is C. It's a gas, so we include it. So C is 2x, and it is going to be squared because there's 2 over the reactants. Concentration of A is 2 minus 1x. It's 2 to the first. Times the concentration of B. It's 3 minus 1x. And it is also 2 to the first. So in order to solve for x, we put this over 1 and do some algebra. But we said, since this K value is so small, we can ignore the x on the reactants. So I'm literally going to go into my formula, the sign, the number, and the x. I'm going to erase it. I'm going to take it out. On my other reactant, the sign, the number, and the x, completely taking it out because I don't need it. The idea is there's going to be such little of a change in the reactant, it's barely going to be noticeable. So it really doesn't matter what the change in reactant is because it's not going to make a difference. It's like if you had $1 million and you gave somebody $1, you pretty much still have $1 million. Whereas the concentration of product is 0. So since it's 0, there's none. And that means no matter what amount you get, it's going to be significant because it will go from being nothing to having at least something. So it's like if you're completely broke, you have no money, and somebody just hands you $5, you now got $5. It may not be a lot, but you're no longer completely broke because you got just a little bit of money. So when this K value is so small, it's not going to change the reactants enough to matter, so we can ignore how much it's changing by. Alright, let's simplify this equation down. So I got 1.0 times 10 to the negative fifth over 1. Is that equal to 2x squared? So 2x squared becomes 4x squared. 2 times 3, well that's 6. That's much easier to do. Now we can cross multiply. 1 times 4x squared is 4x squared. 1.0 times 10 to the negative fifth is going to be 6.0 times 10 to the negative fifth. Alright, to solve for x, we divide by the value with x, divide by 4, that cancels, divide by 4. X squared equals 1.5 times 10 to the negative fifth. Now take the square root. Take the square root. X equals 0.004. Now, we're at the end step. All we got to do is take our x value and plug it back in. So 2 minus 1 times 0.004. So 2 minus 0.004. And I get 1.99 molar. We had a 2 molar concentration. At equilibrium, we got 1.99 molar concentration. Not much of a change. That's why we're able to ignore x. Now you can go through and do it the regular way completely all the way through. You're going to get the same value. So I highly recommend taking the shortcut and ignoring the x, since that value is so small, since that k value is so small. Let's finish it out. So 3 minus 1 times 0.004, which is 3 minus 0.004. I'm going to get 2.99 molar for the next reactant. And for the last one, 2 times 0.004 gives me 0.008 molar. So I went from having no concentration to having a concentration, and that is a significant change, and that's what matters. So that is also an equilibrium problem where you're solving for concentration, except we got to ignore the x and made it a lot easier, a lot faster. We found the same information. But we can only do that. We can only do that if this k value is very small. So in your problems, hope and pray that those problems have a k value of 1.0 times 10 to the negative fifth or smaller. And that is equilibrium, basic equilibrium. Hopefully you were able to follow. If you weren't able to, highly recommend watching the second practice problems video, practicing as much as you can, asking questions when you can, and giving it all that you got. This lesson does take time to learn. It is difficult at the start, but once you got the hang of it, it's just time consuming is all it is. It gets easier. So I hope this video helps, and as always, good luck on your tests.